All right. We still are in extraterrestrial area. We're going to finish that up because that's easier, and then we go on the surface of the Earth and see now what happens there. I get H naught and I naught and all those radiations on the outer skin, and then what happens if we move to the Earth's surface. But as I said, there are a few points there that I need to cover, so let's start with those and then move on. Speaking of which, we also categorize that radiation as beam radiation from the name. So if this was the outer skin of the atmospheric air, and then the sun there, that radiation is all beam. It's from there that part of that then became beam, and the balance diffused. So, and now we are still there. And therefore, the possibilities are that if this is the horizontal line, plane, that is north, south, east, west, we have two possibilities. This is a horizontal surface, and this is a tilted. So it's the same surface. Imagine that we give it a slope of beta. Then under identical condition, let's say the sun is here. You're just doing identical situation. So at one given time and point, we might have the let's say this ray of sun coming, hitting the surface. So here would be exactly a line like this, or parallel to that. If I draw and then we call that G for instantaneous radiation, B for beam, and N if this came from normal to a surface. Now the angle that if I draw a normal to this surface, and call that N, Then per definition, if you remember, this was the theta, the incident angle, versus this case that if I draw the normal to the surface, would be the theta z, that we call that the zenith angle. That's the difference. So this was the z zenith angle. Obviously, if this is the horizontal plane made of east, west, and north, south, perpendicular to that, we call it z. And the angle that the ray of sun made with that angle, we call it theta z, while here, if I draw a normal to the surface, the angle that the normal to the surface made with ray of sun was theta. And we can therefore calculate the ratio of the amount of radiation received by this horizontal surface versus what we call it the tilted surface. So therefore, if I define, the whole point is define this ratio RB, B for beam radiation, because we are still out there, and then this is nothing but a geometric coefficient. B would be, I think to be exact, we would call it factor or ratio, and this B stands for the beam radiation. By definition, this is the ratio of the two G tilted divided by GB. Not tilted, the normal. Namely, we are looking for if I call this normal to the horizontal surface GB versus that one that I call it, this is GBN and this is GB, now that I wrote it on that, T for tilted. Then the ratio of GB tilted, the amount that is received by tilted surface over the amount that would be horizontal, is a ratio that we can find it in terms of the two angles. So therefore, eventually this becomes, if I have GBN times cosine, and this would of theta z, and GBN times cosine of theta on that direction, the end result would be what we have as GBN, because these two are identical, cosine theta to represent GBT, and GBN cosine theta z. GBNs being identical because we are comparing two identical cases, location, then would be cosine theta divided by cosine theta z. And that is what I'm asking you to calculate in homework 1. If, of course, the radiation is normal or in the direction of zenith, right above the surface, then these two would be identical and you get 1. But we can get it from the, we have a formula for cosine of theta by now, and we have the formula for cosine of theta z, and we are therefore able to calculate this ratio. In your book, if you remember, I believe it was 161. Yeah, 162. And for cosine theta z, we also derived cosine phi, yeah, that was cosine, 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 sine, sine. Cosine delta, cosine phi, cosine omega, plus sine delta, sine phi. So normally we have both, and therefore we can calculate the RB. So let's do an example. Location. Tucson, Arizona. August 10th, 3 p.m. local time. Collector has a slope of 60 degrees. That is beta 60 degrees, and it is facing 15 degrees to the west of south. Okay, so a problem like this could, by the way, 3 p.m. is local time. So it's a bunch of information in there that you have, so problem usually is proposed to you as this, and what we want to find is simply RB. And in getting RB, a lot of the formulas that we have been discussing is involved here. First, a little sketch means that if we have the north-south and the east-west, so we would have, let's say, a collectors, hard to show. So it's lifted from the horizontal surface by an angle of 60 degrees, and when I project the axis of the collector, this is the collector axis, on the horizontal plane. So I should make it collector axis projection on the horizontal plane. It makes this angle. This is what we call, this is west of south. Is that what I said? Yeah. So it's on that side, and therefore this is the angle. We recall that was gamma, and that is given 15 degrees.
Can I ask a question?
Yeah.
So the direction is 15 degrees west of south, but which sense of the arrow like? Is it like this or like this?
Are you questioning my drawings? Remember, I'm doing a 2D drawing.
Just asking.
Yeah, imagine, well, let's see if we can. Yeah, those drawings are never to scale and absolutely correct. But if this was the plane that I have there, north, south, east, and west, first of all, this collector makes a 60-degree angle with that plane.
Okay.
So it's not flat, it's like this. And secondly, I have another way to rotate it. And the way I have it, I rotate it just enough that if I draw the axis of this projected on that plane, it makes a 15-degree angle with the north-south.
But if the projection is the same if it's tilted like this or like this. And that's what makes me confused. So I'm just asking which.
Projection, well, you look from the top.
It's the same.
Suppose if you look from this angle down, again, is a 3D plot, but this is the axis of the. Oh, you're talking about this versus that? This is the actual axis of the collector to be this. Okay? This blue line that you see there. And now I'm projecting, looking from the top, projecting that on that plane. And of course, and continue on both directions. You see that this is the one, and this happens to be making 15 degrees. Okay. Now I said that there are some calculations in between. I'm hoping that our technician is covering this part. So let's do the solution there. Now, one thing is, in Arizona, in Tucson, Arizona, they don't have a lifetime, a light-saving time. So that's the only state, maybe one of the states that they don't change the clock back or forth as we do here. Therefore, it just happens that local time is the same as standard. That is no time savings or clock change. Okay, you might have heard that Massachusetts is also thinking about it. I heard the other day, but we still do, of course, go back and forth. If that's the case, then 3 p.m. Local means 3 p.m. standard. Okay, so now we put it on standard time, but we're not done yet. We got to now change it to solar. So we do the procedure to changing to solar time, and to do that, then August 10 corresponds to N of 222 from table 1 there, and then based on that, I'm going to calculate delta we all agreed that we use the simplest formula of 23.45 times sine of 360 times 284 plus n over 365. Okay? And if we do that, simply substitute n here and calculate sine, and delta turns out to be 15.3634 degrees at that time. Then we need phi in these formulas, you saw that. So we go online and find phi for Tucson, Arizona. The tabulated is 32.24 degrees. This is, by now you all have a source to get all those numbers, for if nothing else you need for your homework. So I assume that everyone knows that. Now we need the solar time. If you remember the formula for solar time, the difference between the standard and solar time. I don't want to write something that is not accurate. We need the equation of time to get the E and then put it in the formula, the difference between solar and standard time, and get that and make sure that we use correct numbers. So if I can find it. Okay, here we go. If you recall, we need to find the solar time to be equal to the standard time plus 4 times, and we had 2 absolute values of the standard longitude minus local longitude, both absolute values, plus E. Okay, now we need to find out on what standard meridian Tucson is, and it happens to be on the 75, I believe. I'm sorry, it's 105. And then local longitude, we also look it up, is 110 point. Exactly where you look up phi, you also look up L local, and that is 110.9568. Okay, so those two numbers are where I looked up. And now we can substitute if we can find E. For E, we are going to use the formula 292, the correlation 292.2. And if you remember the four zeros, 75 plus 0.01868 cosine of B. And again, two more terms for cosine and sine of 2b, where b was defined as n minus 1 times 360 over 365. So in this case, I'm going to have 222 minus 1 times 360 over 365. That corresponds to B value of 217.97. Then we substitute B in E, and the end result is that E is minus, by the way, the E that you get out of this formula is in minutes. So when we get that E is minus 5.701 minutes. So we're ready to calculate the solar time. Therefore would be equal to that is the two we were looking for 3 p.m. So is 15 at the hour of 15 plus 4 times, and then standard was 105 minus 110.9568. Then plus minus 5.7. E was 5.701. So this is now minutes, and this is, what is that, degrees over 15. This is also minutes, so the end result would be a negative number, so we're going to subtract from this. This is hours. So the solar time eventually becomes 14.5079 hours. So it was 30 minutes or so difference. All right. Now that we have this in hours, if you like, you can change it into hours and minutes and so on. So this could be hour of 2 p.m. or 14, and then half of an hour, that's 30 minutes, and maybe a fraction for seconds, 0.079 times 60, a few seconds. But that in ours is good enough because now we can get omega out of that. So the sequence of calculation now would be omega, the hour angle, to be time that we have minus 12 times 15. And when you substitute for that, 14.5079 minus 12 times 15, the omega would be 37.618 degrees. All right. Now we can calculate cosine of theta z from that formula. To be point I call this 1 is equal to 0.78737 from equation 1, and we can also calculate theta or cosine of theta. This is from, in the book, I can refer you to equation 162 to be equal to 0.679. By the way, this is equation 1 in my writing here, but is also equation in the book of 165. Text equation 165. So having these two, therefore the last point is that geometric factor of beam radiation on tilted versus horizontal to be 0.8624. So the ratio of these 2 point cosine theta is 0.697 over 7873 to be equal to 0.8624. All right, that's a review of basically everything we've said so far regarding these calculations. Fairly straightforward. Next is that equation 162 that we have been talking about for theta, cosine theta, could be reduced to a more compact form. If you've been reading the book, through a math trick. So we do a math trick and then change the angle so that theta could be more compact. Right now, 162 has 5 terms made up of cosine and sine of omega, phi, delta, bunch. So What it means is that here, if I look at the location on the Earth's surface, okay, and somewhere here I have it tilted. It could be actually on the air skin outside the surface. This could be, again, because we are now dealing with beam radiation, not that it matters, but let's say is because it's the same, it's the continuation of the same beam as long as we talk about beam radiation. So it could either be here at an angle. If it was horizontal, it would be tangent. If it's an angle, then this would be representing a tilted with an angle of beta as a slope. So what I'm saying is, doesn't matter whether it's here or there, the geometry or the formulation or argument would be the same. Again, this is horizontal and that's beta. So, in any event, if I take that here, now imagine that this is, we can rotate it about the center of the Earth. If I start moving this on the Earth's surface, there comes a point that the tilted collector will be tangent to the line and becomes horizontal. So according to what we know, this is phi. Because phi was the angle that a point here would make with the equatorial plane that on the, when I cut it, is a line like that. Now if I start moving this collector in this direction, as I said, there comes a time, a location that the collector is now tangent and therefore becomes like on a horizontal plane. All right. Now, it's mathematically this angle obviously is also beta. So is this angle. Again, one angle that the two sides are perpendicular to another one. That side is perpendicular to this, and this side is perpendicular to that. So geometrically, if that's beta, this is beta. Therefore, this angle is phi minus beta. All right. On the other hand, this a normal to the surface at that point, if let's say the sun was here, I mean its position, relative position to that was here, and we would have a ray of sun to the collector at some point, normal to that. Would be this, and therefore the angle between the two would be theta. By definition, this is the angle of incidence. Now, exactly corresponding to this location, again, the ray of sun would be parallel to this. So we would have a ray of sun parallel to that coming here instead. Exactly same, parallel to that. Remember, although I put the sun here, but in reality, sun is 5 million kilometers away. So when I say these two rays are parallel, they are parallel as they come in. And if these two are parallel, then I would have theta z, because this would be the z, the zenith perpendicular to the surface, and this would be theta z. All right. So we argue that this situation is exactly like that situation. Therefore, theta z would be equal to theta if I use a fictitious latitude angle instead of phi. If I use phi minus beta, then I'm here, so I can imagine that instead of being there, we are here on a different latitude of phi minus beta. So if I want to calculate theta z, therefore, going by the formula that we had for theta z would be equal to, was cosine of phi, but now phi has changed to like phi minus beta. Cosine delta and cosine omega is the same, doesn't change, plus next term was sine of phi, now becomes sine of phi minus beta times sine of delta. Okay, when we are here. But at the same time, this is also theta, because theta z becomes exactly like theta when we are in this position. So from here, therefore, we can say that theta is cosine of phi minus beta, cosine of delta, cosine of omega, plus sine of phi minus beta, sine of delta. This is a much more condensed version of theta. Okay, is pure math basically, but rotating this, bringing here. So what was phi there, here becomes a phi minus beta, and what was theta there becomes theta z, or what is theta z here is the same as theta, and we use that similarity to come up with a simpler, definitely much simpler than equation 161 for theta calculation. All right, this is everything I did is in northern hemisphere. If you do it in southern hemisphere, namely if you start somewhere here and do the same thing, then you'll adding a beta, and therefore theta would be cosine of phi plus beta, cosine delta, cosine omega, plus sine phi plus beta, sine delta. This is if you are in the southern hemisphere. All right? So this is basically pure math transformation. No physics involved. That makes life easier. Okay. Now we want to go back, now that everything about the beam radiation and extraterrestrial coverage is done, I want to go back to the example that we had, and it is in the book as example 191, but I want to go into that maybe a little bit more detail, so we can see exactly what happened, and therefore maybe we can do a little bit more complicated cases of a shadow of a building cast on a solar collector somewhere. Okay, the idea is that in a simple case here, I have a building with open field there, and we have a solar collector somewhere. What we have is that, and we initially have chosen a position S where we put the collector, and that happens to be 10 meters away from the building. We have some information about the building, the height of it, and how expansive it is in the direction of north-south, and we want to see whether this building will cast a shadow on the solar collector that is there, or whether it's a good position or not, and we're going to discuss that. So this is looking from the top. It turns out that if this is all the flat roof building, the building has one height, then we don't have to worry about the rest of it. In reality, there is a wall here that the sun comes from this direction and casts a shadow on the collector. So all we have to worry about is I'm bringing this wall here. And this is the location of the solar collector, and we want to investigate that. Now, to find the shadow of the building over there, generally on the back, we need more than 2 points. Although the building is linear, but there's a little point here, and that is that here I have sphere, and I'm holding a line somewhere in front of it, let's say somewhere here, and then I shine a light behind that line. I don't know how to plot it though, so it can show, but anyway, let's say the line is here somewhere in front of the sphere, and now we are going to shine a light on that line. What is the projection of that line on the sphere? It's not a straight line. You all know it's a curved line. So we may get something like this. That this line being that, and then that one coming from here. So the shadow of the straight line here would be a curved line there. So that is why we pick more than 2 points. If it was a straight line, you would pick a point at this edge and another point at the other edge, and then we will have the entire shadow on that area. But we normally pick more points. The more points you take, the better, but at the same time, you don't want to go crazy. So in this example, as you see, 1, 2, 3, 4, 5 points are picked, and the choice of that is totally arbitrary, as long as you have more than 2 points so you can represent some sort of curvature, that's fine, and it works. So obviously the edges are good points to pick, so we're gonna pick the point to go exactly by the same notation. This is point A, directly drawing a line to the wall, and then on this side C, and in this side we call it point E, because these are the edge of the building and we know all those dimensions. This happens to be 10 meters SA, and SE we can calculate given the fact that we have all these dimensions. Then arbitrarily we pick 2 more points here. 10 meters from A and on each side 10 meters, and we call this point D and point B. All right. Again, why? For convenience, we pick 10 and 10 here, so we can calculate all these angles would be easy. But you don't have to have it exactly symmetrical, just for simplicity. But it could be 20 meters away as long as you have the corresponding angles, and it's okay. Now, these are all on the edge on the top. At the same time, you have corresponding points down at the root of the wall. So that's why I've drawn a 3D. If I stand here and look, this would be the wall that we are facing, standing here at the location of the solar collector. If I put the S here, and therefore we picked E, A, this point, and C here. These are the top edge, A, and then D about 10 meters. By the way, this is 10, 10, this is 20, and this is 20. These are just a given measure. We know the total is 40. So this distance is fixed. However, the middle points we picked that the way you see it. So this is A, D, B, and now if I draw a line on the roof, on the root of the wall or the bottom of the wall, we are going to have the corresponding C prime, B prime, A prime, D prime, and E prime. Okay? By the way, the bottom of the wall for us is defined where the level of the collector is. The collector may not necessarily be on the ground. So remember that if the wall could be as tall as you can imagine, however, the important part is if the solar collector happens to be here, away from the ground, we don't care about this part. The important part is that, and that's when I call it the root or the bottom of the wall is where it is at the same elevation as the solar collector. Okay, so this wall could be further going down, but the point is B prime, A prime, D prime, and E prime are at the same elevation as S. As the point that the solar collector attaches to its platform is good enough as a reference. All right, so the idea is that we calculate a bunch of alphas and gamma, alpha S's and gamma S's, so having the sun charts for that location, if I can find the corresponding values of these angles or in gammas and alphas and put it there, then I can draw a line, a fitted line through that and then find the shadow and determine whether this is a good location or not. So there we go. We have a bunch of angles to calculate. Alpha, I've called it, going by the notation of the book, OE. Can you see that this is 3D? So it's an angle that when you connect S to the bottom E and top E, these two lines make an angle that would be the alpha. Gamma, however, is easier to look at. Gamma, if you recall, was measured with respect to the south-north axis, which we have here, north-south axis. So the angle for this angle alpha for A would be 0, or gamma, sorry, gamma for gamma for this line, OA, we call it, is 0 because this is in the direction of the north-south. Then this represents gamma of non-gamma, OB. Because everything has to be measured from the north-south axis.
This we're assuming that the collectors are on the north-south axis, right? In this example. Okay.
Yeah, you mean the axis of the collector?
Yeah.
If it wasn't, again, it's geometry. You can calculate. You can add that to every angle that you're measuring. He is asking whether this, when I have this solar collector, is axis, when I project it, is also parallel to that. It is. So therefore, this would be gamma OC. And then on the other side, we have some negative values, because now we are on the east of south, gamma OD and gamma OE. So the gammas is looking from the top. Basically, you project everything on the ground, on the horizontal plane, and you just measure the angles. And in this case, is straightforward. That is what is done, namely tan of OB. If that's OB, the tangent is 10 over 10. That's 1, and then based on that, you'll get the values. So let's do a systematic work here. The gammas are easier. Gamma OA is 0. Tan of gamma OB, tangent is 10 over 10. Meters is 1 out of here. Gamma OB is 45 degrees. Tan of gamma OC, and by the way, therefore OD would be minus 45. I'll write it down, but let's calculate OC would be 30 divided by 10. So it's 3, and out of that I get gamma OC 71.6 degrees. Now gamma OD is negative OB is minus 45 degrees, and gamma OE is negative gamma OC, that is minus 71.6 degrees. So I have all the gammas for those 5 points that we picked. Now alphas need a little bit of head scratching because we need to get some length here. Just simply SA right, SA is 10 meters, SB that is a given value. SB is the square root of that, and that would be 14.1 meters. SC going there would be just 30 squared plus 10 squared, square root of 31.62 meters. Again, pure geometry. Now, what is tan of alpha OA? If I connect from the base to those 2 points, okay, the angle that these two make is alpha OA. And alpha OA is, first of all, is a right triangle. You can see it. And tangent to that would be the height of the building divided by SA that I have. I already calculated SA. Do I have SA? Yes, we do. So, what is the height of the building? That's something I should have given you. Two and a half meters. That's the height of the building above the location of the solar collector. Okay, so in a way, this is 2.5 meters. It's one-story building. So tan of OA, therefore, is 2.5 over 10 is 0.25. Out of that, I get alpha OA to be 14 degrees. Tan of alpha OB is 2.5 divided by what we calculated here, 14.1. That is 0.176, and out of that we get alpha OB to be 10 degrees, and so on. Tan of alpha OC would be, again, 2.5 is the height divided by 31.62. That is 0.079. Out of that, I get alpha OC of 4.52 degrees. And similar way, alpha OD is 10 degrees, same as that. And alpha OE is 4.52 degrees as that. So now we have a collection of 5 points, A, B, C, D, E, each with 2 coordinates, alpha naught, alpha OB, and gamma O, and we just put them there, 14 and 0, 10 and 45, 4.52, 71.6. 10 minus 45 degrees and 4.52 minus 71.6 degrees. So the points are complete. Now, what we do, we're going to then fit a polynomial into those. We have 4 points, 2, 4, 5 points. We can theoretically fit a 4-degree polynomial to those points. So next job is, any fashion you know, either go take it to the Excel, plot 4 points, and fit a curve. Go to the trend line and pick a polynomial of 4th degree, and this is what you get. Plot alpha naught versus gamma naught. Actually, limit could go higher, but this is what we had, basically, up to minus 71.6 and plus. So anyway, when you plot these points, you'll have one here corresponding to 14 degrees in the alpha naught axis, and then other symmetric points at 45, minus 45, halfway, 2 other points, and then some more at 71.6. The way we picked our points were symmetric, but they don't have to. You can pick any points you want. Now, theoretically, we can fit a 4th degree polynomial too. When you do that, you get something like this, and they give you an equation in form of you get the coefficient of the polynomial, whether you use Excel or MATLAB or any other package, they give you those coefficients. So then they say you that y, in this case alpha naught is equal to a naught plus a1 gamma naught plus a2. These are the coefficients that the whatever system you use will print for you. I'm hoping that you have done all this before. Gamma squared, a3 gamma cubed, and a4 gamma to the fourth. That is the equation of this. And a1, a2, a3 are the coefficients of polynomial. All right. If you haven't done that, it's a good idea. Go practice in Excel and get those. Why are we doing this? The reason we're doing that is if you just plot those 5 points and you connect them, you get straight lines connected to each other, and it really is not exact shadow. That's one point. The other, and by the way, a third degree will do the job as well. You don't have to go to fourth degree. As long as it's not linear, that's fine. The other advantage is that we can actually extend that to the sunrise and sunset as well. So once you have the polynomial, you extend it until you find the point that the polynomial hits this. So you have the endpoints as well. And once you know the endpoints, then you have more than 1, 2, 3, 4, 5 points. You have infinitely many points, and you can create an array of a lot of points, 150, whatever, but more than what you have there. And this array, this alpha naught, therefore, gamma naught will start from the edges, because now you extend that to whatever point it would be. This n point, for example, on negative side, and this would be n point on positive side, and in between you have so many points. You pick the increment for it. If it started, let's say, with 95, this would be then 90 minus 89, and you can, and then all the way to 90, and then from the polynomial you get the corresponding alphas. And then copy this array and paste on the sun chart. See if we have any luck. Yeah. Okay, this location happened to be at 45 degree latitude. So we already had the sun chart for it. And when you create an Excel sheet or MATLAB for getting a sun chart, then you can create infinitely many by just changing phi. You get the corresponding sun chart. And now you copy the, as you see, I extended the polynomial. Of course, this was for part B that is skewed. That's what I said. Their polynomial is not always necessarily symmetric. This was skewed, but doesn't matter. I fit a curve, extend it to the edges. So roughly, I'm going from minus 70 degrees to plus 110, and that's what you see here. Minus 70 degrees for the dashed line, 210. But the solid line is what I did on the board. I picked a polynomial and then plotted there from edge to edge, and this is what I see. And when we look at it, this is great. This is a perfect location for this. Why is that? Because most of the shadow is only under this line. So when the building is here, it's only cast so much shadow. Therefore, for most of the month of the year, and this is all half an hour, 30 minutes to sunrise, or half an hour, 30 minutes before sunrise, you might have a little bit of shadow on certain months of the year, but the rest is okay. All right. Now, what is the dashed line? The dashed line is part B. That now I'm sure you can follow that. It's a little bit more involved. Now, what happens if we tilt the building? What if the building is not exactly north-south, east-west location? If it's an angle, it tilts. And if the building tilts, then all your alphas and gammas change. And in this case, it didn't change much. It did a little bit. So as you see, the end polynomial is that, and when you plot it, would be the dashed line. So maybe a little bit more shadow here from that side of the sun on the building. But still, this is a good location for that solar collector. However, we have examples that this line ends up being there, something like that, and it happens. The other, okay, let me finish that. You got the idea. Here, the part B is when you tilt. So actually, the building is like this. You still have the north-south the way it is. Of course, that did not change. But the top wall is now that. So same point distribution is done. However, we have to calculate the angles a little bit differently. And in my notes, I explained that the one-handy formula, we remember the sine law for the triangles. So this is part B of the example that I'd like you to follow the notes. And when you do that, because the triangles are not right triangles anymore, you need to make use of the sine law. That is let's say we had a situation like that, then according to sine law, I don't want to insult your intelligence, you already know all this, but just a reminder that is a typical triangle, then the sine of A divided by the face, the side that is facing that, SB is equal to the sine of B divided by SA that is facing it, or equal to sine of this angle S divided by the AB that is facing. Okay, and that comes, every pair of them comes very handy. If you have the length, you can get the angle, or if you have the angle, you can calculate the length. So this is very useful for a problem like this when the geometry is a little bit more complicated. That's one thing. Secondly, we only had one elevation here. However, it could be that a building with an elevator shaft that is sticking out of the building, the air conditioning room right on the top, other blocking okay, so the building is there. However, it just so happens that something else, a huge extension of some sort let's say with the solar collector somewhere there, then the points that you pick are important. Obviously, this begs for a couple of points here. So in this case, I would probably get maybe A here, B on this edge, C there, and then D there. If you're looking for 4 points, or maybe one more point somewhere over here. And if it's even more than that, if it's another high sticking chimney or something over here, then you might have extra points. But that's all right. As long as you have the dimensions, the height and the width and all that, you should be able to calculate alpha and gamma corresponding to each and every point. Okay, and once you have that, then you fit a polynomial through it, and you find that whether this has any contribution, doesn't. It gives you an idea of whether B and C are making it. Depends on maybe at some location, some time of the day, the ray of sun hitting B and C hits the ground before the solar collector or after the solar. But anyway, these have to be taken into consideration. Once you have that, again, you can cast the shadow and on the sun chart and see the location. So a judgment here is important, is where to take. And you may end up actually having more than one set of choices for the points. See which one is the worst scenario case. All right? So that's that. for a few minutes that is left. We're going to then talk about the reality or the amount of radiation now we get on the Earth surface. The actual radiation, solar radiation received on Earth is, of course, the most accurate way is to measure. As simple as that. If you can afford and you have the funds for that, you want to have a solar system here, a thermal solar system here, you spend 6 months, a year, if you can, and then collect data exactly at that point, and then that is the amount. Then there are models, and of course, if I get that amount for year 2019, there is no guarantee that it would be the same for year 2022 and so on. So there are formulas and models that kind of predict what's going to happen. But the more data, the better, and that's why we have centers that they do that for one thing. They have 50-year data, and therefore they do some statistical analysis to kind of predict from the past performance of what you're going to have at any given time. And for most of these problems, you will do that. I'm asking, for example, what is the amount of radiation received by a solar collector in a certain location on Earth, and then you hopefully locate that location and the data on whatever is owned by government or private companies who are willing to give that data out and get what is there. And some of those, just a small list of that, WMO for World Meteorological Organization. That is one good source to go. Look it up on the Google it, and NREL. You heard of that? Yeah. If you have been working in the National Renewable Energy Lab. NOAA, you heard for sure, National Oceanic and Atmospheric Administration. And NASA, of course, has a lot of data for their own purpose, and a few others. So it's not really limited to that. The other day I was talking about the solar constant, and we talked about another organization that was the National Radiation, something like that, World Radiation Community, WRC. So there are several of them, but you can get what you want from an organization like that. Now, when we use this throughout the book, there are some notations that we want to make sure we all understand, and that is anything with subscript naught, as we explained before, is extraterrestrial, and G happens to be instantaneous. Whatever you get at that given time. H naught, again, we discussed that daily. Extraterrestrial radiation. For or on a particular day, because it's daily, then it could be from day 1 to N 365 on a horizontal surface. This is normally in megajoules per square meters. We already did a formula, derived a formula for calculating that number. While I'm at it, I want to tell you that, of course, that formula is accurate for much more accurate than what we have here, because in a table, but nevertheless, the table comes handy just for sanity check. If you notice see if I can bring that table up. Here we go. Someone decided to, for every 5-degree increment, calculate that H naught for you. I'm not going to go in details over the number, but at least you can see that this is table 110.1. That the formula that we derived the other day, the integration formula for H naught, use that, but just for the sake of having some reference point, started with 90, went all the way to minus 90 with increment of 5 degrees. So, for example, if we have some numbers that are not exactly 65, but if you were at a, let's say, 55-degree latitude in the month of May, the H naught would be 37.6 megajoules per square meter. Now, I say it's a sanity check because you might be at 55.4, so at least when you integrate and you get a number, your number must be very close to what you read here. So it is just a reference to make sure that the number we're calculating is correct. But they all come from the formula, the integral formula that we derived the other day. But it could come handy when you want to check your numbers. Time is over, so we're going to stop here and continue